We're looking at section 15.2. We're going to be graphing logarithmic functions. So the graph of the logarithmic function, f of x is equal to log base 2 of x, which we analyzed in the previous lesson, is shown. So we're going to analyze and graph some other basic logarithmic functions. So the key thing to keep in mind here to remember is that the logarithmic function is the inverse of an exponential. So log base 2 of x is the inverse of the function 2 to the x. So if you can graph 2 to the x, which should be pretty easy for you to do, all you have to do is take those coordinates and switch them, okay? And that's going to be your inverse function, your logarithmic function. So this time we're going to graph f of x is equal to log of x. Now remember that when the base of the logarithmic function is not specified, it is understood to be 10. So we're going to plot and label our ordered pairs. So again, we're looking at log base 10 of x. And that's going to be equal to y. So each time we think about these, we're thinking of 10 to what power is our x value here. So x value here is 1 over 10. So 10 to what power is 1 over 10? That would be -1. Anytime you're changing, if you've got a whole number versus a fraction, your exponent is going to be negative. So for the next one, 10 to what power is 1? That would be 10 to the 0. And then 10 to what power is equal to 10? That would be 10 to the 1. So these are going to be our coordinates here. So at point 1, we've got a coordinate at -1. At 1, our value is 0. And at 10, our value is 1. So we're going to have an asymptote at 0, x equals 0, our y-axis there, and then our graph is going to look something kind of like this. So we're going to complete the table for the function f of x equals the natural log of x. So remember that this is a function of base e, and then plot these points as well. So again, we're thinking it's log base e of x is equal to y. So when you circle the wagon, what this means is that e to the y is equal to our x values. So we're thinking e to what power is 1 over e? That would be -1. E to what power is 1? That would be e to the 0. E to what power is e? That would be e to the 1. And e to what power is e squared? Well, that would be 2. So these are our points here. Again, we're still going to have an asymptote at 0, x equals 0. We're going to have a point at 0.4, -1. It's about there. Point at 1, 0. A point at about 3, 1. And then a point at about 7, 2. There it is. So this graph is going to look something more like that. So if we want to analyze these graphs and compare them to log base 2, so we graph log base 2, log base 10, log base e, the domain, x is greater than 0 for all of them. The range, this is wrong. This should be -infinity to positive infinity. And -infinity to positive infinity is the same thing as all real numbers. And behavior. As x goes to positive infinity, f of x goes to positive infinity. And as x goes to 0 from the positive direction, f of x goes to negative infinity. I'm not going to fill out the rest of these tables because everything else is the same. It's all the same. Everything here is the same. All of these properties are the same. They have the same domain, range, and behavior. Vertical asymptote, intervals where they're increasing and decreasing. They're going to have the same intercept, and they're going to be positive and negative in the same areas. So what similarities do we notice? They all behave the same. The only key difference is something we're not really going to deal with now, but it's important when you move on to calculus. They have different rates of change. So they'd have different slopes as you graph them. And you can see that when you look at the graphs, which ones are changing more steeply versus, so comparing, let's say, log base 2 versus log base 10. The log base 10, the values are increasing much more slowly. It took us from 1 to 10 to x value wise to change 1 vertically. So that's the only thing that's really different among these graphs they're going to have the same types of behavior, just different rates of change. They're changing at different values. So when we graph these, we're going to have the same types of behavior as we've seen before. What would we be multiplying them by? If we multiply by a negative, it's going to reflect it. Multiplying by a number that's a fraction, it's going to compress. A number bigger than 1, it's going to stretch. Inside of the logarithm here is going to be your x changes, and then outside is your y changes. The main difference here, your asymptote is going to be going along with your x values now. So instead of before it was y equals k, it would be your asymptote. Here it's going to be now x equals h, because instead of a horizontal, we have a vertical asymptote. The reference points are also similar in the, let's say, the 2 to the x. The reference points were 0, 1, and then 1, 2. So 0, 1, and then 1b. Our reference points are, again, the inverses. So reference points now are at 1, 0, and then b, 1. So the base 1. Those are the 2 reference points you'll want to use for the inverse functions, the logarithmic functions here. So we can take this function, see what's happening. So we're multiplying by -2. So we're going to have a stretch of 2, and then the negative is having us be reflected across the x-axis. Inside the function here with the x's, that's going to do the opposite. We're going to move to the right 2, and then outside we're going to move down 2. So we'll apply those changes to the 2 reference points, 1, 0, and then the base is 2. So the other reference point would be at 2, 1. Domain is now changing based on your x values changing. Your range is always going to be all real numbers. Domain is going to change based on your vertical asymptote. So now it's going to be x is greater than 1 since we shifted to the right 1. So here, when we look at this one, we want to think how our x and y coordinates are changing. So our x values, we're going to do the opposite. We're going to subtract 2. Y values will need to get multiplied by 2 and then add 4. So reference points are at 1, 0, and then our base, comma 1. So notice here it just says 2 log x plus 2. So we've got an understood base of 10. So our other coordinate would be at 10, 1. So 1 minus 2 is -1, and then 0 plus 4 would be 4. 10 minus 2 is 8, and then 2 plus 4 is 6. So we're also going to have an asymptote at x equals -2. Remember, it's based on now your x values. So those would be the coordinates. You'd graph those there. Domain, x is greater than our, oh, sorry, that's the original graph. We need to graph ours. Sorry, vertical asymptote at -2, coordinate at -1, 4, and at 8, 6. So graph looks something like that. Domain, x is greater than our asymptote, so greater than -2. Range is all real numbers, hasn't changed. All right, last one here, and then we're going to be all done. So we think about how our x and y coordinates are changing. So x values, we do the opposite, so we'll subtract 1. Y values, we're going to multiply by 1/2 and then add 2. So reference point 1, 0, and then reference point of our base. Our base here is 2. So base 1. So 1 minus 1 is 0, and then 0 plus 2 is 2. 2 minus 1 is 1, and then 1/2 plus 2 is 2.5. We're going to have an asymptote at x equals 1. Oh, sorry, -1, because we're subtracting 1. And x equals -1 is our asymptote there. So we can plot that. X equals -1, coordinate at 0, 2, and then a coordinate at 1, 2.5. So it's going to look something like that. Domain, x is greater than our asymptote of -1. Range is all real numbers.